Hi, my name is Muthu Aravoli. I'm a rising senior here at Duke studying electrical and computer engineering. I'm the electronics team lead, and because of this, I worked on designing and integrating both the hardware and software aspects of our sensing and perception subsystem.
Hi, my name is Yuri Chen, and I'm a junior majoring in biomedical engineering. I work on developing the hydrofilm systems to locate the underwater acoustic pinger.
My name is Brandon Bay, and I am an upcoming sophomore majoring in electrical and computer engineering along with computer science. In the Duke Robotics Club, I am a member of the electrical subteam that specializes in setting up communication between our hydrophone system and logic processor.
Hi, I'm Nick Chakraborty. I'm a rising junior here at Duke studying computer engineering and physics. I'm co-president of our robotics team, and I work with the sensors in designing our robots' control software.
Here's an overview of all the subsystems involved in sensor optimization. First off, we have the state estimation subsystem. The overall goal of this subsystem is to estimate the current pose and twist, position, orientation, and velocity of the robot. To do this, we input data from an IMU, inertial measurement unit, a DVL, Doppler velocity logger, and a pressure sensor. We fuse this data together using an extended Kalman filter. This gives us the estimate of the current state. We publish this to ROS, providing a standard interface for higher level code to use. We also have cameras as sensors in our robots. These cameras allow us to gather visual data about the objects and obstacles around the robot. As part of our system, we have two cameras mounted side by side in a front-facing direction. We use these as a stereo camera, allowing us to perform depth perception calculations on obstacles in front of the robot. Our cameras connect with the computer on our robot via Ethernet, and they connect to the rest of our software system by using a Python-based hardware driver we use to send images to ROS. These images are then picked up by our custom CV pipeline, which then processes and analyzes, determining the objects in the image. Our acoustic subsystem consists of two separate sets of hydrophones, each used to sense the acoustic waves that the underwater pingers produce. One set is used primarily for making a quick guess of the quadrant relative to the robot that the pinger is in. This is then used as input to our processing algorithm. This algorithm uses the other set of hydrophones to make an accurate determination of the location of the pinger. To actually sample the hydrophones, we use a Salier Logic 8. This allows us to simultaneously sample the hydrophone set. This connects to our computer via USB, and we have Python hardware drivers that interface with it. To simplify the overall external-facing acoustics interface, we provide a simplified ROS action for higher-level subsystems to interface with acoustics. Next, we'll talk about how each of our subsystems influence our overall competition strategy. With regards for sensors needed for state estimation, as mentioned before, we use an IMU, DVL, and pressure sensor. For the IMU, we use a VectorNav VN100. This has an onboard Kalman filter in the hardware itself that inputs the angular velocities and provides us with the orientation of the robot. Our DVL is a Teledyne Pathfinder. It provides us with linear velocity data. We don't use the linear acceleration data from the IMU. This is because our DVL provides the linear velocity. We found that by using our raw DVL data, that it's more accurate than integrating the linear acceleration provided from the IMU. We'll also use a pressure sensor, a Blue Robotics Bar 3 that gives us pressure data, which we convert to depth. We've noticed that this drastically helps our depth hold. We use static transforms extensively in our state estimation subsystem. Our static transforms package is the sole location of mechanical details about the robot, including the location and orientation of the sensors. This means we can place sensors in whatever position and orientation we want, and we only have to change the values located in this package. The static transforms are all relayed to the TF2 package, which publishes them to ROS, which allows the rest of our system to access them. Our sensor fusion and robot localization package is the package that actually integrates the sensor data to perform the state estimation. This package also keeps track of our current state as the robot moves from position to position, publishes this current state to ROS for use by any higher level packages like controls or task mining. To do this, we use an extended Kalman filter to perform the actual fusion and localization. We chose an EKF over a UKF because we found that the EKF had better performance. Any higher level tasks that require any sort of movement all make use of this sensor fusion and robot localization. For our cameras, we use Allied Vision Mako cameras enclosed in a waterproof capsule. We have a total of 3 cameras. 2 front-facing cameras are sampled synchronously to allow for them to be used as stereo cameras, which allows us to do depth perception, which is useful for many tasks, such as the gate task or any task that use the claw. We also have a downward-facing camera that we use for tasks that have pointers or targets on the floor, such as the task to drop an object or to identify path markers on the floor. We decided to implement stereo cameras only for the front-facing cameras. Since we don't really need depth for downward-facing tasks, we can always pitch the robot if need be. We chose to use Ethernet to connect it to the rest of the system. It also allows us to stream data at high data rates. With regards to the software we use, we developed an interface that allows us to use cameras from different manufacturers. This allows us to easily switch and add cameras during competition if need be, even from separate manufacturers.
To localize the pinger, 2 separate hydrophone arrays are used. The first array is less precise and collects data to rapidly create an initial guess of the pinger location for our acoustics processing algorithm. The second array is more precise and collects more accurate data to use in our acoustics processing algorithm. These arrays run in parallel to facilitate faster processing time. The arrays have a tetrahedral configuration, which enables accurate localization along the X, Y, and Z axes, and the hydrophones are placed in specific locations, which avoids noise from propulsion and maximizes the distance between the less precise hydrophones in order to generate a more reliable guess.
Closely intertwined with our hydrophone sensors is our Salia device, which is a logic analyzer that simplifies the process of converting the analog signals from our hydrophones into digital signals that our algorithm can analyze. However, what sets apart our Salia and hydrophone setup to other systems is the Salia's capability to sample signals across 8 channels simultaneously. This allows us to sample all of our hydrophones in parallel.
Our sensor optimization is well equipped to handle the tasks at competition. The robot localization system works well for the gate and buoys, so we give those tasks a 5 out of 5 confidence rating. We give the bin and the torpedo task a 4 out of 5 rating. While we believe our robot localization is good enough to position the robot in the right place, there are other concerns like propulsion and task planning. We are confident in our acoustics package ability to find the pingers, so we don't think our robot will get lost. The only very difficult task for us is the octagon. We give it a confidence score of 1 out of 5. Our sensor system is actually likely good enough to find the bottles and position the robot over them. But again, there are concerns with the claw mechanism, control system, and task planning that we could not overcome.
First off, we're going to take a look at the pressure sensor. This sort of acts as an example for the rest of our sensors. And so to actually implement this, first we wrote our custom sensor driver code and added that to the existing Arduino code. You can see that in the first picture on the bottom left. We then wrote a Python ROS node that converts the pressure to the depth, that converts the pressure from the pressure sensor to the depth of the robot. You can see that in the bottom right. And then we also wrote code for our simulation to take the depth of the robot from our simulation and publish that to ROS, thus mocking the existing pressure sensor code. And so overall, this is how we have to implement every sensor. We write our custom driver code, any conversions that need to happen, and then for an implementation of the simulation to work with that. With regards to sensor fusion and robot localization, we have to write any driver code for any new sensor. That's what we just went over. And then we add any relevant static transforms to this launch file down here in the bottom. And then we have to add them to the localization YAML files shown here in the right side of the screen. All right, so now we're going to demonstrate the robot sensor fusion in action in our simulation. We use Copelia Sim as our simulator with a custom ROS wrapper to interface with the rest of our system. Our simulation will mock the sensors we have on the robot and will publish the appropriate values to ROS. So the simulation is started. With this, we can notice that we actually have 3 different sensors that our simulation is simulating: the depth from pressure sensor, the DVL, and the IMU. So we can see from this the data that the IMU is publishing. And so this will correspond with the location, the orientation of the robot. So our actual sensor fusion algorithm, it publishes to the state topic. So we can see it changing as time goes by with how the robot is moving around. And so this just demonstrates our sensor fusion. So overall from this, we can see how sensor fusion inputs data from our sensors, in this case, our mock sensors, and then outputs the state of the robot. All right, so now we can take a look at our depth hold. And so we can see here that our robot, it goes into depth hold and does it really well. And we found that the pressure sensor was the reason why it does this. It's able to just consistently hold that depth. Here we have a stream from our stereo cameras, namely the left and right stereo cameras, the ones that are facing forward. And you can sort of see how they're offset slightly, left being a little bit to the left, right being a little bit to the right. And you can see how they how they update simultaneously.
Due to COVID, we were unable to obtain actual hydrophone data in pool tests. To overcome this problem, we wrote code that automatically generates artificial hydrophone data for both hydrophone arrays. The code simulates the data that the hydrophones would pick up from a pinger at a specified location, and it adds noise to mimic the competition environment. In addition, we also wrote a wrapper that can seamlessly switch between using artificial data and using real hydrophone data.
Much like the testing situation with the hydrophones, the virtual format of this year's meetings prevented us from testing a Saley device in conjunction with the entire hydrophone system. Since we couldn't test our Saley device and hydrophone set together, we put in mock signals through the Saley device in order to make sure it could properly sample analog signals. Additionally, we utilized the Saley device's built-in signal simulator to simulate random analog signals as well. Now that we are slowly returning to an in-person format for meetings, we plan to test the Saley while it is connected to the hydrophone and collect actual acoustic pinger data in order to see how the Saley would do in a competition setting.